For this plane strain condition, let's start with a simple example. Let's say that we have a structure of a dam. A dam is a structure that actually blocks water across a certain length, generally placed in front of rivers, very large rivers, so that the water cannot flow across it, and you let it through only when you need to. So basically you can control the flow of water. Now let's say you have the three different axes in certain direction. We assume that, or we assume whether the dam is actually quite long in the direction Z. That means it continues over this length for a long distance. Then it is supporting water which is coming from this direction. There's a lot of water which is applying a lot of pressure on this side of the wall. And what you also see is that the cross section of this dam remains the same across the entire length. So considering these three different conditions, we can classify this as a plane strain problem, because for a plane strain problem, a body needs to be long, and by long I mean quite long as compared to the other dimensions. And that's true for the case of this dam because it's quite long in the direction Z. The second one is that the geometry of the body is more or less constant in the length direction, which is also true in this case. And the third one, and the final one, is that the loads are also more or less constant in the length direction, which is also true because you have the load or pressure because of the water on the walls, and it is the same across the length, or let's say more or less the same across the length. So any body, for example, if there is a cylindrical body and it's quite long, and the only load we have is a certain load from top, which is across the length the same, and the cross section also remains the same, and it's quite long body in this direction, it can also be considered as a plane strain condition. And to model these different sections, we can just reduce it to two-dimensional planar surfaces which look like this, and plane strain conditions attached to them. So if you remember the plane strain condition that we did for the one before, for the plane stress condition, when we reduced the matrix, the stiffness matrix, then it looked somewhat like this. Actually, this is not the one for plane strain condition. This is the one for the plane strain condition. And I can resize it and put it here for you so you can see it. So in this case, we know that strain is equal to C times stress, and this is the reduced C for a plane strain condition. Now the same way, when you want to make a plane strain problem, you follow the same path as you did in Abaqus for the other problem. For the plane stress problem, that means you do the 2D planar, you apply a solid homogeneous part, you tick on the plane strain condition, and in the elements you define the plane strain as the element you want to use. Now what if you are using Patran? If you're using Patran-Nastran, then you actually have 2D plane stress and plane strain property types. So you look for these property types in Patran-Nastran when you are making 2D properties, and you would be able to find these as direct conditions, and therefore you would be able to apply the property type directly to your part. So it's basically quite simple. The difficulty here is that you have had to make sure that you've made the right assumptions and that you're able to reduce a certain part into these cross sections, which is it can be quite tricky, but in the end, if you see the change in computational effort that you have created by instead of making this huge dam with solid elements and how many thousands of elements you would require to just this surface, which is quite easily meshable with 2D elements and very fast computed, then it definitely makes a very big difference. But make sure you choose the right assumptions to make sure that it is indeed a plane stress or a plane strain problem.